Hello and welcome back to the lab. A huge thanks to all the Patreons that help make this channel possible. And if you're discovering the channel for the first time, welcome. And for everybody who's returning, welcome back. Today on the bench, we have another of the TM500 series. This is a double wide module. Unlike the AA501s, this has 2 card slots in the Well, that's going to need to be addressed. Didn't notice that before. Bought it untested, so it is what it is. Today on the bench, we have a PG508. It is a pulse generator for the TM500 frames. Double wide, 2 circuits in the back, but it doesn't require a TM5000. This can go into TM1000. So we'll be doing a restoration and alignment on this. I'll crack the sides open, see what we're getting into. We're gonna have to work on that card edge connector for sure. That'll probably be a job for the 3D printer, so I'll have to model something to get this up and running again, at least for small parts. We do have a 3D printer in the lab, so we'll be able to take care of that. There are some, just from doing a once-over, there are some giant electrolytic caps in here that I'd like to address. Get those swapped out with something a little bit younger and fresher, because no shelf queens. I want everything to work. So let me get this thing torn apart and we'll take a look. Well, here's our first look, and it looks like we have a bit of crust. Definitely have some dust, dirt, grime. Gonna have to get off. Actually, that's be nice if it's that easy to get off. I could just get it off with an air gun. Wouldn't have to argue with it too much. At least on first pass, ooh, couple of decent sized power resistors that I might need to check from the other side. Got a couple of electrolytics here and here, and I've got these 2 big ones that I want to replace. These are probably in the power supply. So these will have to go. This one's got a bunch of corrosion on the end of it, so on the other side, let's take a look. Well, a lot of ceramic and a lot of tantalums, but not a lot of, oh, this one's set to 50 ohm input impedance. We can set that to 1 meg or 50 ohm. That's switchable. Definitely have to clean these switches per normal. Actually, cap-wise, this thing doesn't look that bad. Polys, some ceramic disc. This is a poly. I won't have to change him. Another poly up here. Can I get to all these cam switches to service them without... I'm staring at the top. Maybe it won't matter. It doesn't look like removing these back 2 boards, as long as I remove them as a set, that they'll be too terrible. Not seeing any heat damage. Everything looks good. Alright, well, we got a game plan. Let's see what we can do. Holy cow, they buried the switches under here to clean them. The good news is you only have to take 1 knob off, but then this entire assembly comes out. That exposes these 3 cam switches, these 2 relays, and there's another cam switch hiding back there that I have to get to. So I'm actually going to separate these 2 boards. I'm going to pop this one off, and that'll expose the barrel there so I can service that. After that, even though we don't have a board holder yet, it'll be at the point where I can force feed this into the power supply so we can at least power it up, see if it works, or if we have any more troubleshooting to do. I'm kicking around how to 3D print a holder for this. I still have to design it. A Fusion 360 is something that I am not proficient with, and the learning curve's pretty steep, so that is where we're at there. The knob you have to take off is the transition time knob. Everything else can stay because it's got a adapter on the front. Here's the front of unit. That's what's left when you pull the sideboard out. These are the main filter caps that I've already replaced. They were pretty chunky. These are 2200 by 30. These are 4700 by 50, and they're 105 degrees C rated, so they should be fine. Trying to think if there's anything else. I don't think so. Everything's going pretty well. Yeah, so I got to pull these 4 screws off to get this board separated. When I put this back together, I will go through where all the connectors go and everything like that. If anybody watching the channel takes one of these apart, that way it'll help you get it back together again. That is the easiest way to get in trouble, is to just rip one of these apart and then go, how does it all plug back together? And digital pictures are amazing for that. I take a ton of pictures of all of these. They end up on the Patreon page when the video goes live, so anything I took as a tech photo, I throw those up there. But yeah, on to switch cleaning. This is the bottom side of the power board. I have to look at the schematic because I really kind of want to know what this is doing here. There's this weird contraption of power resistors that are just, it's 2 resistors, and everything in here is in parallel. I have no idea what this is doing. So, yellow, violet, brown. These are all low ohm resistors, or I mean black. So these are extremely low ohm resistors. But yeah, this whole assembly is in parallel with each other. So I have no idea what this thing is doing, but it's bizarre looking. The other thing to be careful of when you pull this top board off to expose the switches, there's these 3 pass-through pins. These are very delicate when you put the boards back together. Don't bend these. Okay, I have the board back in. Everything is good. So, or I have the boards back in. Everything is good. I got to make those feet now, or the card edge holders. So I've got to spend some time over at the computer. The program I use to do that is Fusion 360. It'll allow you to have 10 active models and a few other things for free if you're a maker. You just need to set up an account and you can download it, at least as of the recording of this video. But so that's step 2, or that's the next step. So on to that. Well, after a number of iterations of these board clips, I managed to get some in, and the board's held in like it's supposed to. It flopped around in there before, so that's nothing abnormal. This is the original that was in there. It's actually spring-loaded. The ones that I made are more rigid, and actually holds it in a lot better than these did. It's much more secure with these new ones. These were a couple of failed attempts just for various reasons. A couple of these were even prototypes. Yeah, this one didn't even have the holes in it. I hadn't put the holes for the screws in there yet. That one's got them. But 3D printer made some new board mounts. That's in there nice and secure. That is the correct orientation. The connectors towards the bottom. I have to double check one more connection. This one right here. And then I should be ready to do a smoke test, and hopefully it doesn't blow up. I don't even know if it works yet, so I have to hook it up and see if there's any signs of life. I haven't even powered this thing up yet. So, but we're making some progress. Everything is looking good. The controls are clean, serviced. The switches are serviced. Everything is good to go. We have offended it greatly having it that far apart, tearing it down, putting it all back together again. So I am going to have to do an calibration alignment on this, but that is what it is. It's just something I got to do. Not a huge deal, but we'll get... I need the top cover off anyway to do the alignment, because there's a pod right here I'll have to adjust, and a few others. But, yeah, let me see what's going on, and we'll see if we can get fired up. Okay, I have the power analyzer turned on, so let's see what kind of current we're going to draw. I've got the scope turned on, because if everything goes well, and it doesn't, I'm not expecting anything to happen, but if it doesn't smoke out, then we'll see if we can get some pulses out of it. Drawing about 50 watts. No lights on the front panel. Get a coax line. All right. Output to here. Sorry about bobbling the camera. Take this off so you guys can see it. And we should at least get a... And there's ground. All right, let's see. Transition time, slow. Faster period. We actually want free run. And no delay. And let's see. And we're lowering wattage. Well, the power light's not on, so that's a bad sign. So we are not powering up fully. Let's see what's going on. We are drawing some current, though. If the power light's not coming on, it's going to be toast. So let's see what we got. Well, my negative 15 volt supply doesn't exist. Or my positive one doesn't. My negative one does. I am getting voltage at the bulk capacitors, so my rectification's working and the power supply's working, but without the plus minus 15 volts, none of the op amps are going to turn on, nothing's going to work. So, gotta go digging. Gonna pull up a schematic, gonna take a look at the power supply section on this one, see what I can figure out, but we're gonna be into some troubleshooting on this one, because the power supply looks like it might be kind of toast. It's also drawing still about 40 watts, so I'd imagine something's getting kind of warm. So now the real question is, if I shut it down, do I have like a shorted tantalum on my power rail? Do I have... I don't know what I got yet, so we shall see. I definitely want to get this pulse generator working again, because it'd be nice to add to the lab, but it's gonna need some repair. Okay, one immediate clue as to what might be going wrong. This component is incredibly hot. I touched this rail and I damn near got burnt. So this is probably dissipating my entire 50 watts, which is what I was seeing. So, I'm gonna pull him off. I was kind of curious about this when I was taking it apart, because there was not an insulator in between this component and the chassis. I second guessed that because it looked like it had been there for a while, because the dust pattern looked like it had been that way, but this may be bad. So we'll definitely check this. This is of interest for sure. And this might be shorted out and dead. If that's the case, we'll replace that. This is definitely... Is this cooled down yet? Yeah, that's cooled down. So we'll throw him on a curve tracer or the component tester and we'll also find out what he is doing in circuit. But first suspect is this guy right here. Okay, after a bunch of troubleshooting, we found a shorted tantalum capacitor. This little bead of tantalum popped off. I don't know if you can see it on camera, but it was on the outside of this cap. It got knocked off while I was moving stuff around. And this guy is most definitely cracked. It is not going to show up on camera, unfortunately. So, got that all hooked up. And let's see. If we sanity check it, let's see if we get a power light. Lights flashed. Hey, we have a power light. So, very cool. Progress has been made. So now it's on to checking the power rails and making sure we can do a calibration on it. This was killing the 15 volt rail. So the way I found that was I injected some voltage from one of my power supplies into the 15 volt rail, nowhere near 15 volts, but I gave it a decent amount of current, and it slowly started to kind of recover, and then I heard this real faint pop, and that real faint pop was this tantalum letting go. It's just a decoupling cap, so no big deal there. I got it replaced with a 47 microfarad electrolytic, and it's working just fine. This is a 20 microfarad tant, so gave it more. It's a 35 volt cap on a 15 volt rail, so it is just fine. The unit ran just fine last night, all night. Not all night, but for most of the evening. And we didn't have a burn down, nothing else decided to go bonkers, and it stayed powered up. So I think we're ready to attempt a calibration. I have the adjustment locations printed out from the service manual. And this one's going to be a little weird. I'm going to have to go lots of places in the lab because I've got the 7603 warming up. I've got the 2 multimeters warming up. Frequency counters warming up. But I'm also planning on using the DSA 70 or the DSA 602 for this one. I have it, and I've got the 300 megahertz plug-in. This is only a 50 megahertz pulse gen, so well within calibration for that. But the time base on the DSA 602 is infinitely more accurate than the time base on the 7603. So the service manual calls for a 7704, which is a 200 megahertz scope, 300 megahertz plugins with an incredibly accurate time base in the DSA, so we're going to use the DSA. I will not be able to get the DSA in the shot while I'm doing the adjustments, so I'm going to have to move back and forth between the two. The main problem is the DSA itself is just absolutely gigantic. The scope is humongous, weighs 90 pounds. So it sits on the shelf over there and doesn't move because it weighs a ton. So we'll get the setup in the preliminaries. So triggering is free run, which is out. Undelay, which is in. Period is 2 milliseconds. It is. Calibration. I did check. The cal knobs are rubbed off on this one. Calibrated, there is no detent on this one. I'm not sure why, but cal is all the way counterclockwise on these buttons. So there's no detent on this one, but all the way counterclockwise is where that needs to go. Delay should be 10 nano. Duration is square wave calibrated. Square wave and calibrated. Transition time is 5 nano. Leading trailing is both 1x, so 1x is over here, 100x is over here. This is an infinitely variable control, so 1x. Output volts is normal. High level is +5. Low level is 0. It just wants me, the next part of the step is just verifying that these knobs are correct. I'm just going to do a quick check on those, sanity check, because I didn't have to take these apart, so these should still be correct, but let me just double check that real quick, and I'll be right back. Well, it turns out the knob does need to be adjusted just a little bit down here, so what we'll end up doing, because if I move that up, that right there is 0, because ground reference is here, so I do need to adjust that just a touch. Well, that was incredibly fiddly and took way too much time, but I got the knobs adjusted. If yours are even remotely close, don't take them off. That is an incredibly fiddly setup. Okay, we're checking the 5.2 volt test point. Ground is over here. 5.2 volts is actually hiding behind that ceramic capacitor for me, right where the 15 volt regulator plugs in. And we're looking for 5.2, and I gotta find out what my accuracy is. We're at 5.20. We'll see if we can touch that up just a bit. A little bit. Okay. Leaving the controls the same on the front. Let's check the +15, which is right here. I need 14.25 to 15.75. 14.82 is fine. And negative 15.10 is fine as well. Next up is adjusting the 2 microsecond periods. Okay, the frequency counter is off. Up here, we can actually see it counting up. So I'm going to let that stabilize with temperature for a little bit. That should read 500 kilohertz. It is still moving a touch. It is on the external reference. The potentiometer we need to adjust is this one right here, which is R186. Once that stabilizes, I'll come back and do the adjustment. All right, we'll do the adjustment here real fast. Here we go. I'd like to eke out one more significant digit. Hey, I got 2. All right, that'll work. All right, we're adjusting the symmetry. So let's see, I need trigger. And if I move slopes, it's a little more this way and a little less that way. So I need to adjust the symmetry a little bit. That is R180. So the symmetry adjustment is R180. It's right here. It's just a little off. It's not too terrible. Let's see what we can do. That's vertical. I'm actually going to need to do this adjustment on the 7603 because of it clipping. You guys can't see it, but it's clipping the waveform a little bit right here, which is causing it to throw this off. So what I need to do is I need to warm up the 7603, get that working, and then I will be back. Well, I'm at a standstill. One of the reasons I was fighting with that adjustment was the symmetry pot just decided to come apart. So I have to figure out what part I need to get to replace that. There's where it should be. So I will need a new control. Oops. I have the new potentiometer installed. Everything is good. Here's the old one that's out of the unit. So we'll toss that into the dish of shame. And then we will continue on. I've done the symmetry adjustment. It's an incredibly fiddly adjustment. You have to bounce between the variable time base, position sensor, and the adjustment on the PG508. This is not a specified parameter, however, so you get it as good as you can, but exact perfection isn't needed for this one. The way you test is make sure the scope is in DC. If it's not in DC, you won't get the transition that you need, but then with the scope set up one period of the waveform, you flip it back and forth between negative and positive. And you want this transition to be as small as possible. So if it's way over here, that needs to be adjusted. If it's way over here, it's got to be adjusted. But you want the center transition to be as small as possible. And I'm running about 2 divisions, 0.1 division on each side, which isn't too bad. So the next step is to adjust the 20-second period. I'm going to do I'm going to use the frequency counter again for that. So I'm going to move back to the PG506 and we'll get set up for that. Okay, so free run, undelay, period is 20 nanoseconds calibrated. Delay is 10 nanoseconds. Duration is 10 nanoseconds. 1x, 1x normal. And we do this on the trigger output. So we move that over. Bring this up to the frequency counter. We need to adjust R195, which is this side of the unit, all the way on the back of the main board. I'm going to move everyone up to the frequency counter, and we'll do the adjustment. And we want 51.5, so we're off just a touch, not too bad. Hopefully this potentiometer doesn't fall apart on me, so I don't have to replace another one. I don't want to have to wait for the mail again. Oh, wrong way. There we go. Oh, I'd like to get one more. Ooh, that'll work. All right. 51.5. Now, the calibration document is saying to adjust the first period, whatever that means. Triggering is going to be plus slope. Undelay. 2 microseconds. 10 nanoseconds. Duration is square wave. Transition time is 5 nano. 1 norm. Oh, my there you go. 5 and 0. Okay. Okay. After racking my brain against that for a little bit and what they were trying to do, they're using the delay and the magnification on a time base to adjust the period at 500 kilohertz. I'm going to use the DSA. I've set the DSA up to measure period and frequency. I'm just going to tune the frequency to 500 kilohertz. So we'll just direct measure it. Okay, I needed something a bit more accurate than even the time base in my DSA, but that is about as close to 500 megahertz as we'll get it. So there we go. Okay, that last calibration routine that I did, that was not the way to do that, and I now know. So I thought it was just setting a period. It's not. I have also been asked by Patreons and a few other people on YouTube if I'll leave the mistakes in, so that's why I'm leaving the mistake in. Here's what it's actually doing. So I'm going to turn up the B sweep on the 78, or on the 7854. Actually, we'll turn up A sweep too. And we'll set this to chop. And give me some trace separation. Move this up, move this down. So I've got the 7B80 triggering at 1 microsecond. No. And then I've got this at 0.5 microseconds to give me this waveform down at the bottom. This is the one I'm going to focus on, so I will bring that down, and we'll bring this up. So what it's doing, this is the front of the gated pulse. I'll adjust this. What you're going to see is you're going to see a ghosting on the waveform. I don't know how well it's going to show up in camera, but I will tweak the potentiometer here real quick. Yeah, there it is. So we get this ghosting on the waveform. What I want to do is I want to line that ghosting up with the actual waveform. So what we'll do is we'll just bring this back like so. And there we go. So that's step 7. The next is adjusting the first period on the 20 nanoseconds. So I'll get that set up, and then I'll bring you guys back. I'm going to continue using the 7854 for that. Okay, as a confirmation, I did the 20 nanoseconds, and it is the same thing. I'll tweak the 20 nano right now. And it's right there. That's what I'm looking for. Okay, we'll set up for step 9, which is the 1 microsecond and 10 nanoseconds durations. So, free run, undelay, 2 mic, 10 nano, 10 nanoseconds, duration 1 microsecond. Duration 1 microsecond. Calibrated, calibrated, calibrated. Transition time 5 nano. Output volts normal. All right, external trigger out to the external trigger of the scope. Set this up for external, A trigger, B's off. There we go. One thing to note is it says use a 50 ohm terminator. I do not need to use a 50 ohm terminator due to the fact that I am actually using a 50 ohm input on the scope. So having a 50 ohm terminator is not immediately needed because I'm using a 7A19. I take that back. The 7854 is not going to be fast enough. I need a sampling scope, so we'll kick back over to the DSA. Okay, this one's pretty straightforward. 200 nanoseconds per division, which is 200 micro, or 0.2 micro. Yeah, 0.2. And we want a duration of 5 divisions. So what I want to do is we're going to set up, turn the touchscreen on. We're going to set up averaging, small bit of averaging. 64 averages will be fine. That cleans that up quite a bit. And then what we're going to do is I want to be on the horizontal. And that's right there, so I want to pull that in with R470. R470's down here, bottom of the main board, left side of the unit. Okay, let me look at a scope, figure out why that's collapsing like that. It shouldn't be doing that. Okay, there we go, finally. 200 nanoseconds, 5 divisions of display. That one's set right. That one fought with me. For one of the reasons that it fought with me was I missed the period, changing the period from 0.2 to 2. It should be 2 microseconds, not 0.2 microseconds. That caused problems with the unit. So it did want to use a sampling scope for that, so that's why I moved back over to the DSA. Next up is the 10 nanoseconds duration. So we have to change the period to 20 nanoseconds, or sorry, 20 nano. Duration to 10 nano. Period cal knob to about 45 degrees. And a sweep rate should be 2 nano per division. There we go. So this needs to be measured at the 50% points of the waveform. We'll turn on a cursor. All right, and we'll call, let's see. Cursor. All right, so my cursors are here and here. And we want, for a duration of 10 nanoseconds, so a duration of 10 nanoseconds would be 2, 4, 6, 8. So 5 divisions in total. Then we actually need to expand a little bit. The duration, 10 nanosecond duration, is this potentiometer right there. So we actually need to move this out. 5. I need to bring this point in just a little bit. I'm actually too slow. Let's see. I'll turn averaging off. Waveform. Cursor's on. Yeah, there we go. Okay, let's see what this does. Oh, I see why that was being so difficult. Okay. Yeah, the cursors, given the way that's moving, when I adjust it, the cursors are going to be no... cursors aren't going to do me much good. Okay, that one was pretty hard to do around the camera. So, what I ended up doing is using the scope, I adjusted up and down and left to right till I got about the middle of the waveform on the center line, and then I just adjusted it for 5 divisions, which is where it wanted to go. But it's really fiddly because when you adjust it, the waveform shifts up and expands, so you have to bring it a little bit down, and you just have to keep bouncing back and forth between the sampling scope and the pot, and the sampling scope and the pot, and the sampling scope and the pot. So, but eventually, that's what it ends up with. Okay, time to adjust delay. So we want free run undelay. Period is 2 microseconds, not 0.2. Delay is 1 microsecond. Put that back to cal. Duration is 0.1. Transition is 5 nano. 1 and 1. Normal and correct voltage. Alright, what I need to do, I need to get 2 lines of the same length because I'm adjusting delay, and this coax is actually going to act as a delay line. That's not the same length, that's too long. Be right back. Okay, getting this one set up was also a fight. This is one of the most fiddly adjustments that I've done. This thing's worse than doing a scope. This thing is really fiddly, actually getting all the adjustments done right. I'd prefer to be working on a scope, even though they're longer. Alright, so references here. Here's the channel 1 pulse. This is the channel 2 pulse. This is the trigger out, so we're adjusting the delay. So what we want is, this will be 1, 2, 3, 4, exactly 5 divisions. There we go. That is setting the delay. Okay, so for the top and bottom clamp, this one's okay. What you do is once you get everything set up, you want these transitions to mirror each other. So this one actually looks pretty good on the scope. Everything looks pretty healthy. Okay, got everything set up for step 12, adjusting the transition times. I found a typo in this service manual. On step E, it says adjust set trailing. Well, and then it tells you to adjust R650, which is here, which is for the leading edge. This is set in the next step, so you want to adjust R650 first, then R542. So these are on the bottom of the unit. So what we're going to do is we're going to adjust the leading edge for 500 nanoseconds. And I'm using the scope with the rise time calculators down here, rise and fall, to do these adjustments. There are the cursors showing how it's calculating. And let me put some averaging on. And measure. That'll clean it up just a bit. These were off. These needed to be adjusted. Okay, here we go. That's about as good as we're going to get the rise time. Fall time, which is now trailing edge, which is R542. We also want to be 0.5, so going to adjust the trailing. There we go. Nice. Okay. So I've adjusted the rise and fall times. Those are here on the timing board, and we actually get to those through the bottom of the instrument. So right now I have it sitting on its side. Okay, this is a strange setup. I have to take the normal, and then I have to short the center conductor of this switch together. All right, now what we need to do, move over to the scope. All right, we need to zoom this out so we get it started. Okay, it may not be triggering. Let me move this over to the 78, and I'll see what I can do from there. I have to find the waveform on this one. This whole calibration's been odd, but this step's odd in particular. Could have done this with the meter, but set my ground reference, which is here, DC, and it's finding something. All right, found a signal finally. No wonder I couldn't dial it in on the other scope. Okay, so what we need to do is we need to adjust the NC balance R910 right here for minimal signal. Ooh, that's a touchy control. And right there is going to be about good. Actually, you know what? We could. Too noisy. Okay. Okay, because this one isn't weird enough. Ground, positive of the voltmeter to the center terminal of the switch. I need to adjust the output volts low control, which is the front control here, for a reading of 1.33. I need a smaller screwdriver. But we're at 2.17. I'm sorry, it's the output low level control. It's the low knob on the front. Okay. Okay, I need to move the voltmeter to the top center pin. Now I'm looking for a high level control of 3.87. There we go. Okay, R885, which is right here, gain, needs to be adjusted right here. Needs to be adjusted for 10 volts into 50 ohms. I've got a 50 ohm terminator on the plug. It is a little light, not bad, but we'll tweak it. It's a touch light. Right there. Just checking the high level, low level tracking. So the way this works is controls are exactly the same as step 13. So reset the output level, hold the low level, and then move the high level. And the low level shouldn't move, which it's not. It's staying nice and stable. Now we're going to do the same thing with the low level. We're going to move everything up, and then so the high and low level tracking is good. Those don't need to be adjusted. If those needed to be adjusted, it would be these two potentiometers down there. Let me check the offset real quick. Need the voltmeter again. Okay, turns out my offset adjustment doesn't need to be adjusted either, because this is DC on the scope. So it's right on the center graticule. I have the low level set to 2.6, so says my 6500. If I flip the scope to DC, it doesn't move. stays at ground, so it actually moves up, which is expected. So the offset is good. I'm going to check the output impedance, but given the way the last couple of adjustments have gone, I don't think that's going to be a problem, but we will see. Okay, setting everything up. I've got, this is where we're at. So we put the 50 ohm terminator in there. Oof, that's way off. Okay, I need to adjust, let's see, R1020. So we need to adjust R1020 for 10 volt. I'm sorry, 5 volt. Yeah, it's 10 volt on the meter, 5 volt on our... Okay, that's much better. And it's this one. Check the Okay, we're going to play with some rise time. We want the fastest rise time we can get. So the PG506 is set up. This is into the sampling scope with a 10x attenuator because it's a 20 volt peak to peak waveform with on 200 millivolts per division. We're looking at this top corner. We want this as fast as we can get it without ringing or other unwanted spurs in the signal. To do that, we're going to play with R150, which is right here, C1024, which is right here, and R1024, which is right there. So let's see what this all does. First up, we're going to adjust R150. All right, we're going to turn on some averaging, but we're going to slow this down. We want 4 averages will be fine. See, I'm getting a spike, so we want to bring that back down. Next is going to be C1024. See if we can get this faster. Oh yeah, we can get it faster if we adjust the cap some. We go, oh no. That slowed way down. That's quick. Nope. Let's get quicker. Alright, now I'm going to adjust R1024. Ooh. There we go. I like that. I'm going to bring this down just a bit. That's much better. All right, what did our rise? Nope, sorry about bumping the camera. What did our rise time get up to? I should have measured it beforehand, but yeah, rise time's sitting about 6 nanoseconds, so that'll work. Last step is doing the error control light, so let me get set up for that. Okay, so I have everything set up. The amplitude I'm measuring is about 12, so I need to reduce that by 10%. So I want that to be around 11.6. Okay, there's 10 volts peak to peak, which is what we wanted. Now we drop this down to 9, so we turn up the leading edge till it's gotta bring it back. There we go. Now I need to adjust C749, which is on the bottom of the unit. I'm missing something. I think it's a 50 ohm terminator. Okay, so mine didn't flash with the trailing edge, so it wants me to do a leading edge again and just get it to the point. So I got to spin this control. Oh, there it was. There it is. There it is. So I am above a 50% reduction. There we go. My capacitor broken? I don't think so. There it went. Okay, we got it. Okay, I redid, with the camera out of the way, I redid the trailing edge just a little bit, and we do get control errors right at 3.1 over 5 volts, so we're good. We're within spec. Barely, but we're within spec. That is a very touchy control. This whole thing's touchy. Thanks for stopping by the lab today, taking a look at this PG508, the pulse generator from Tektronix in the TM500 frames. The parts that were replaced on mine were the 2 bulk caps, these filter caps, the pot died, and then this tantalum was completely shorted and dead. And that's what killed the unit in the beginning with the 15-volt rail. So some of the upgrades we did to this unit, adding some thermal paste to the voltage regulator on the rail, which is now dissipating a lot of heat through the chassis again, which is good. Doing a full adjustment and calibration on the unit. This particular unit was fiddly. I'd rather work on a scope all day long than one of these. Now that I've done it, the second one wouldn't be too bad, but that one was interesting. All right, thanks for stopping by, and I will see everyone in the next video.